Buenas tardes. Good afternoon.
Good afternoon.
Thank you for coming. Studied a lot from yesterday to today to understand the basic concepts of this presentation. Okay, I'm going to make a short review of the last slides of our session of yesterday. Okay. Well, I'm going to present now the physical model of the MOSFET. So the MOSFET is a four-terminal device, and the main parameters for this device are the so-called long channel parameters. Okay, and the long channel parameters in our model are the specific current, the threshold voltage, which we have calculated yesterday. I gave you some numbers and how to calculate the threshold voltage, right? And the slope factor. This is not the electron concentration now. You know, there is the same letter is used for both the electron concentration and the slope factor. From now on, N will always be the slope factor. This is an important parameter of the MOSFET. The main normalization parameters are the thermal voltage, around 25 millivolts at room temperature, the thermal charge density, which is positive for p-channel devices. Because in p-channel devices, the holes are the carriers, the holes, right? And for n-channel devices, this normalization chart is minus NCox by P. Okay? And I have defined the specific current. The specific current is given by this term multiplied by what we call the aspect ratio of the transistor. It's the ratio of the channel width to the length. Okay? And this ISH, or the specific sheet current, or the square sheet current, is given by this formulation here. It depends on the mobility, the field effect, Cox. Also, this N here, which contains information about the depletion capacitance, or CB, and also depends on the thermal voltage, depends on the square of the thermal voltage. Okay? And I defined yesterday the specific sheet current when W equals L. It's a square when you see from the top, W equals L. This is a square, right? So we have this IS equal ISH. This parameter is not a constant. It depends on the gate voltage. It depends also on the temperature. And of course, it depends on the technology. No, mu is a function of the technology. Cox is also a function of the technology. Right? For more advanced technology, Cox is increased. Cox is smaller. Mu decreases with the more advanced technologies, because in more advanced technologies, usually the substrate is more doped. Okay, the doping concentration is higher. All right. Any question here? May I go on? Okay. Now, in order to derive the MOSFET equations or the current in terms of voltage, we built this capacitive model, and from this capacitive model, we can derive the dependence first of the inversion charge on the voltages and then of the current on the voltage. But first of all, we must derive the equations of the charges or the inverted charge density in terms of voltage. And this relationship is what we call UCCM, Unified Charge Control Model. That is how the charges are controlled by the voltage. And you have here two voltages. One of them is inside this term, it's VP. VG is included in VP. Let's now say that this is pinch-off voltage. Okay? VCB is the channel to bulk potential. The channel, we will have two voltages in the channel, which are immediately identified, the source voltage and the drain voltage. Okay? QIT is a reference charge minus NCox phi t. Okay, this is our normalization charge. And VP is approximately equal to VGB minus VT. So this is a technology parameter, and is also, well, it's an almost constant parameter. Say 1.1, 1.2 for more advanced technologies. Okay? Finally, we can normalize this equation and write this charge in terms of the normalization charge QIP, and this becomes a very simple expression. But look here, we don't have an explicit expression for QI in terms of the voltage. We have the voltages in terms of the charge, okay? So there is an implicit relationship between voltages and charges. Okay, but this is very simple to solve. There are several algorithms to solve the inverted charge if you know VP and VCB, right? Let's move to the next slide. Okay, normalized with CCM. And we have two interpretations for weak inversion or the subthreshold region and strong inversion. What's the meaning of weak inversion? Or the inversion charge is very small. Say, what's small? This small is the normalized charge. QI much less than 1. This means weak inversion. In this case, the charge is an exponential function of both voltage, of VP and VC. But look that VP is a function of VGB minus VT over N, and N is greater than 1. Okay? And you have VC here. Oh, this is a simple expression. This behavior is similar to the behavior of the bipolar transistor. There's an exponential region. Here's the charge, but you know, in the bipolar transistor, the current is an exponential function of the voltage. Okay? And for strong inversion, the dominant term is the linear term. This one here. Oh, sorry. This one here. And the natural log disappeared. Or is not very significant for a strong inversion because the linear term is dominant. So in this case, the inversion charge density is a linear function of both VP and VC. Now this is just doesn't have you don't have to care about this because this is just some numbers that say that, well, if QI is less than 0.22, this expression is good. And for QI greater than 20, oh, this is good. In the middle is what we call moderate inversion. Okay? This is not a precise, it's not an accurate definition. Just to establish some limits. Well, if QI is less than this, you have weak inversions. If it's more than that, it's a strong inversion. In the middle, something that, oh, you have to take into account both terms. Otherwise, you have a great error.
In CBDs, the moderate inversion area is a gray area.
It's a gray area, yes. But
It's extreme to define.
it depends on the customer. It depends on the customer.
It's the best definition of moderate inversion area.
What's gray? What's blue?
Yeah.
Dark blue, light blue. Well, you choose. Okay, but this is very interesting because sometimes we are very deep in weak inversion, say 0.1, 0.05. Then I like to use this formula, and sometimes QI is 50, for example. Well, I use this formula. It's not so bad. Okay. So now we have a means of finding the inversion charge in terms of voltages. Now we need to describe the current. For the current, we need what we call the transport of carriers. The transport in semiconductors has two possibilities. Drift, this is the action of an electric field over a charge, and the other is diffusion. Diffusion is due to the motion of carriers. Carriers tend to go from the place where they have a higher density to the place where they have a lower density. This is a very well-known phenomenon in semiconductors. Okay, I explained yesterday a bit about this phenomenon. If somebody is smoking here, the smoke expands and occupies all the room.
Yeah, the ground law.
Okay, and this is a very well explained phenomenon by Professor Albert Einstein. This is one of the most famous papers. He published this in 1905. 120 years ago, almost 120 years ago. This year is called the Annus Mirabilis, because he published maybe the three most important papers in the history of physics about the photoelectric effect, about the Brownian motion, and about the relativity theory. Okay. But this is a summary of what we did so far. And now we can apply this expression for the four terminal device, which has now source and drain. One limit of the channel is the source, and the other is the drain, as shown here in this drawing, right? Just to recall you, this direction is y for us. This is x. Okay? I'm going to show the equation for the current, so I need to define this axis. This is the y-axis, because the current flows this along this y-axis, okay? Oh, maybe you have some dispersion, but in the MOSFET model, it's assumed that the current is very, very close to the interface. This is called the charge sheet model. It's a thin layer of electrons that is responsible for the current between source and drain. Okay? Okay. Now, this is a more accurate expression for the pinch-off voltage. Look here, the pinch-off voltage is a function of the square root of Vg minus Vdo plus something squared minus 2 phi f. Okay? But this expression can be approximated by this one. I don't use this. I don't like this. Okay, I use this, it's much simpler. And as you'll see in a future slide, this is a very good approximation, a linear approximation. Oh, what? There's a square here, but there's a square root here. So you have a, well, probably a good linearity to represent this square root square. Okay? This is a numerical example. Okay? In fact, since my expression in Q is not explicit, I started from here to get this values here. Okay? And then let's start with this Q S equal to 0, 0, 1, and assume that VDB is 0. Okay, so VSB is also 0. Look, you have the source. This is the source, right? And this is the substrate. You have a short circuit here, so VSB equals 0. So in this first case, you have both charges at the source and at the drain with the very same values, because transistor is a symmetric device. Okay, if you have both at the same charge density, you have this node equal to this one. Okay, so in this case, you don't have a current. I'm not calculating the current, but I'm just anticipating that there is no current, because this is like a resistance, the same voltage at source and drain. You don't have, the current is equal to 0. Okay, so in this case, VSB equals 0, so VDB is also equal to 0. Then I use that expression to calculate the VP. So in this case, VP equals QS or D minus 1 plus natural log of QS. Just plug the values, the value of QS here and here. And I found that VP equals minus 146. What's the meaning of this? Well, the pinch-off voltage is negative. The pinch-off voltage is okay. What's the meaning of a negative VP? That the gate voltage is less than VT, right? In this case, VT is 0.5 volts, 500 millivolts. Then, from this value, which is found from here, I found VT equals to minus 146 millivolts. I multiply this value by N and I add VT, and I find that VGB is 318 millivolts. Okay? So VDB is also equal to 0, since I impose that the drain charge density is equal to the source charge density. Okay? So this voltage equals this one. Now let's move to another case. Say, for example, what happens when QS equals 1 and QD equals 0.1? The meaning is that this node here, QS, has a charge, inversion charge density, which is higher than that of the drain, right? So the drain voltage in this case is greater than 0. If you increase the drain voltage, the transistor becomes, say, with a smaller inversion charge density at the drain. Okay, so you have a, let's draw the, what would be the channel profile, something like this. Let's put some charge here, okay? And the charge density at this end of the channel is less than the charge density at the source, okay? So I once again, I calculate the VP, and I find that, look, here, this value VGB equals exactly the threshold voltage. So we have a simple interpretation of Q equal to 1. It means that if the source to bulk is equal to 0, then the gate to bulk voltage is equal to the threshold voltage. This is one of the main definitions of our ACM model. Not a definition, but it's a value through which we find the parameters of the transistor. I'm going to show this in the future and on Friday probably. Okay. Now I just plugged these values in that expression, and I found the values. But look here, in this case, VSB is always equal to 0. Okay, so this term is always equal to 0. And then I find the pinch-off voltage through this expression. And then I find VGB using the approximation of VP, which is VGB minus VP over A. I could do this example from this side to that side. Okay, but for me it was simpler to enter the charge values and then calculate the voltage. In fact, this voltage is 0 for the source, but not for the drain. Okay, so try to understand what this table means. Okay, but this is just an exercise to understand the meaning of that formulation, right? Okay, this is a plot of the pinch-off voltage. Oh, how do you measure this? Oh, it's not the purpose of my presentation now to say how do you measure this curve. What's the VP? VP is, well, is a parameter, but which depends on VGB. But how do you measure VP? Yes, there is a simple circuit which we have used it to measure VP, like this. We impose a current equal to IS. How do you determine this IS? Oh, I have another method to determine the specific current. Okay. And then, in fact, it's 3 IS. Then I measure the voltage at the gate versus the voltage at the source. Okay. In fact, this source voltage is what we call VP. In this case, this is the. I will not explain this right now, okay? But in the future, I can show this equality between ES and VP. But in this graphic, we have the pinch-off voltage VP in the y-axis and the gate voltage the x-axis. And you see that the linear approximation is not so bad. This is a straight line here, dash dot, and the real line here. You see that, well, the approximation is not that bad. Okay. How do you find the value of n? N is the derivative of the pinch-off voltage. of the peak of voltage in terms of the gate voltage. Or better, the derivative of Vp in terms of Vg is 1 over n. Okay, because Vp is a constant. Okay, Vp is a constant, so the derivative of Vp versus Vg is n. And you see that n, you read n on this axis here, the right axis. And you see that the variation of n is more or less between 1.2 and 1.7, 1.8. But this is a transistor of an old generation. Maybe, I don't know, but it made 0.6 micrometers technology, 600 nanometers, something like that. I don't remember exactly what technology this is. Okay. Now, I'm going to explain how we derive the equation for the drain current. Okay. This is why. Okay. The drain current is composed of two terms. The first one is the drift current, and the second one is the diffusion current. The drift current is the motion of carriers due to an electric field. Okay, let's call this EY, a field in Y direction. Okay. The second term is the diffusion, which is due to a great concentration of carriers. Gradient. This is a one gradient in one dimension. Okay. You have a relationship which is called Einstein relationship, which is this is a what we call diffusion constant, which is related to the mobility through this relationship. So I can use this here. Okay. And I can also write the electric field in terms of the surface potential. What's the electric field? Is the derivative of the voltage, or minus the derivative of voltage. So if we assume that the current is in a very, very thin layer, very close to the oxide, then I can say that this potential here is the surface potential. Then I can write the electric field in terms of the surface potential. Okay, so this minus, the electric field is minus the derivative of the voltage with the position. Now I have the two components of the current. Now I'm going to solve this differential equation. I'm going to write this differential equation such as this one here. And I'm going to integrate both terms from source to drain. Okay? Why this this variable here changes from 0 at the source to L at the drain. Okay? Well, I need something here, but I have a relationship that I gave before, which is the relationship between the convergent charge and the surface potential. Now I can replace the surface potential here, divided such as NC ought dq prime I, dqi, sorry. Now this differential equation becomes very simple. On the right side, I integrate from the source to drain. On the source, the invergent charge is called QIS, QI at the source, and that at the drain, QI at the drain. Okay? Now, I can solve this differential equation. Look here, QI times dQI. This is the integral of this is QI squared over 2. This one is QI simply. Then I can replace with the limits and find a final expression, which is this one here. Okay? This is just the solution of that differential equation. Now I have written the drain current. On explanation here, I assume that this current at the drain, it's the same current at the source. So you have continuity of the current along the y-axis. So you can remove ID from this integral, right? ID, and this integral becomes simply L. Okay? Now I have formalized an expression for the current in terms of the charges at both ends of the channel, at the source and at the drain. And now I have UCCM. What's UCCM? UCCM gives the relationship between these charges and the voltages. So we have built a model because we have the current in terms of voltages now. So we have to describe the behavior of the current in the MOSFET. Okay? So ID in terms of charges and charge in terms of voltage, given by UCCM, Unified Charge Control Model. Right? This first terms corresponds to this one here, which is drift. And the second one corresponds to diffusion. Okay? So this is, I would say, the most important result of our analysis. Okay, we have a description of the current in terms of voltage, but we have the charge in the middle. Okay? So it's very important to know about the charge because charges also define capacitance. But this is a subject of a future session. Okay? Any question? May I go on? Okay. Okay. Now we can normalize currents as we did with charges. I love normalization. Okay. And write this equation in terms of the normalized charge and the specific current. I'm not going through the algebra. It's very simple to find this expression, right? And here this is, I would say, a scaling factor of the current, right? I gave this expression before. This ratio is called the aspect ratio, and the notation for this ratio is usually S. I can also rewrite this expression in terms of two currents, one associated with the source and the other associated with the drain. Look here, the symmetry of this expression. If you exchange source and drain, the current doesn't change in absolute value, just changes sign, right? If you exchange source and drain. Say that you have 1 volt here, 2 volts there. Now put 2 volts here, 1 volt there. The current is the same, but the direction is the opposite, correct? Or opposite. Okay? So this is a very important property of MOSFETs, which you don't find in bipolars, because bipolar, the usual NPN transistor is an asymmetrical device. Dopings are different, right? The base is not uniformly doped, so you have different. You don't have symmetry as in the case of the MOSFET. Right? Now, I'm also writing this expression in a different way. I'm going to say that, well, the drain current has two components. One is associated with the source. This component is called the forward current. And the other one is the reverse current associated with the drain. Which properties of the drain? Which property? No, the inversion charge density. And I can normalize this result as well, divide by both IF and IR by IS, and write a small I here, a small IF and a small IR to represent the normalized forward and reverse currents. And they are related to the source and drain normalization, normalized charge through this expression here. Okay? So look here, this is very powerful way of relating currents to charges. You have, of course, to convert charge in currents, you need the transport factor, which is mobility. Okay? Okay, now we have a set of equations which relate voltage to charge and charge to current. The first one is the UCCM. You have a relationship between charge and voltage. Okay? The second one, you can replace the charges with normalized currents. IF, small IF, and small IR. The expression is exactly the same. I just replaced these Q's with I's, right? And here you have the normalized current, ID divided by the scaling factor IS, given by these two terms, which represent the term at the source and the term at the drain. Okay? What do we do for a PMOS transistor? You can use exactly the same equations, but you can do two things, or you invert the right-hand side, or you invert the left-hand side. Just I would say let's use this minus sign here. Okay, but you can also put the minus sign here, then if you invert this expression, it will be VBS and VG and VBD. And the other one, VP, would be VBG plus VP. Okay, but don't invert the two terms, otherwise you have the same expression as in the n-channel device. Okay, sometimes I call this term here VP minus VS V. Sometimes I call this F of IF or IR. To avoid writing that complete expression all the time, I just say, oh, this is a function, a capital letter F here, which represents that function here. Oh, sometimes it's very boring to write that expression on the time. Sometimes you have a lot of equations. Oh, let's simplify and put the result in the final line of my develop my analysis. This is the same table as before, but now I'm also giving the value of IF. No, just IF and IR. Simple expression. Oh, you can write it different. I love this expression. I could write yes, 2PS plus 1 minus 1. This. But this is more interesting, I would say more useful. Of course, they are the same, but I write like this. So if you have, for example, what happens to IF when QS equals? Look, this column is related to this one here. IF is associated with the source, and IR is associated with the drain. It's like in the bipolar transistor. You see that the one term is associated with VBE, the other is associated with VBC in bipolar transistor. So here we have this association as well. IF is related to QS and IR is related to QD. Okay? Look, this is what we call a long channel model. What's the meaning of long channel model? When you see these two expressions, it's like saying that, what happens to the source does not affect what happens to the drain, and vice versa. I can look at the drain, I can look at the source, I calculate everything at the drain and at the source, and then I combine the two effects and find the current, right? This is the meaning of the long channel device. When you have the short channel effects, what happens to the source may affect what happens to the drain, vice versa. Okay? Of course, the current depends on both conditions at source and drain. Of course, at the gates. So, for this column, you use this result here. For this column, you use this one here. For example, if Q equals 1, IF equals 3. It's simple to see 1 plus 1 squared 4 minus 1. Okay? This is a very important number for our calculations because if IF equals 3, means that QS equals 1. And for VSB equal to 0, the value of VG is equal to VT. This is one way to find the threshold voltage. Okay? Not, I haven't shown the circuit to determine the threshold voltage yet. Okay, let me give you some graphical interpretation of the forward and the reverse array. Okay, this is a very simple DC model of the MOSFET. The gate is open. It's a DC model. You have just a capacitance which couples the gate to the substrate. So no current here. Two diodes. Yes, we have diodes. PN junction here, another PN junction from substrate, source, and substrate to drain. So two diode junctions here, and a current source between drain and source. This current source has two components. IF is controlled by the source, and IR controlled by the drain, or drain conditions and source conditions, which of course depend on the gate voltage. Okay? Well, what else? Oh, the bulk current. In our model, right now, we are assuming that the bulk current is always 0, because these two junctions are reverse biased or zero biased. Okay, if it's reverse biased, oh, it has a current. But in our case, let's assume that it's negligible in comparison with the base current of the MOSFET. Okay? So this is a now ID versus VD for a constant gate voltage. So let's interpret this characteristic. Well, Vs is not equal to 0. Here, say Vs equals 1 volt. Okay. When Vd equals Vs, so the conditions are at drain and source are exactly the same. So the current is 0. Okay. Okay. In our case, the conventional current will be from drain to source. If the drain voltage increases with respect to the source voltage, you have a current from drain to source. Look, the current is the conventional one. It's the displacement of positive charge. Now, you don't have positive charge here to carry the current. You have negative charges. But the negative charges move from the source to the drain, which is equivalent to a current of positive charge from drain to source. So if Vd is greater than Vs, you have a positive drain current. On the other hand, if Vd is less than Vs, you have a negative current. Okay, this is the 0, so you have a negative current, right? Now let's see what happens if I keep increasing the drain voltage. Let's keep the source voltage constant. Source voltage is constant, say 1 volt. The gate voltage is also constant, I don't know, maybe 2 volts. And I'm changing the drain voltage. I'm increasing the drain voltage. Okay. And now I make the drain voltage greater than the source voltage. So the current is increasing. Okay. But let's see what happens according to our model. Let's once again. Think in terms of charges. Okay. Now, I keep the source voltage constant, the gate voltage constant. I'm changing the drain voltage. Say, more than 1 volt, 1.5 volts. What happens to the drain charge here when I increase the drain to voltage? You see, the channel becomes less concentrated on the drain terminal. So you have something like this. That's something like this. So divergent charge density is less here than there. So what happens? This term decreases relative to this one, the source, and then the current will start to, well, it increases. At a certain point, this term will become very, very small. Okay? I would say that at a certain point, QD is much less than US. Okay? So what happens then? The two components of the current, IF and 10 ohm, oh, yes. The two components of the current depend on conditions at the source and conditions at the drain. The charge at the drain is decreasing. At a certain point, the drain charge is very, very small and doesn't affect any longer the reverse current relative to the forward current. Then the current kind of saturates. This is the saturation of the MOSFET. Okay. Of course, this is not a real curve, because in a real curve, in a real transistor, that curve doesn't saturate effectively. It's just I would say, a false saturation. It continues to increase, but this is due to short channel effects that I'm going to explain later. Okay. But in this model here, the current saturates. That's it. Okay. So if the current saturates, the drain current has two components, IF and IR. Okay, what's the meaning of current saturation? This component becomes much less than IF. Okay. The meaning here is the following. In the saturation region, I can measure the forward component of the current. So, if you are not changing the conditions of the source, in this curve, the source voltage is constant along the whole curve, I would say that at each point, the drain current is IF minus IR. The component which is varying here is IR, which depends on VD, while IF depends on VS. So if I measure a drain current here, and if I already know the value of IF, I can conclude that this difference is due to IR. Oh, what's the meaning when VD equals VS? Oh, ID is 0, but because IF equals IR at this point. When you decrease the drain voltage, the drain current becomes negative because IR becomes greater than IF. So this is very interesting to interpret this kind of curve in terms of the forward and the reverse curve. But you should keep in mind that the determination of the forward current is here at some saturation of the characteristics. But in the real case, you don't have this real saturation. You have something similar to saturation. But assume that this curve varies, say, not less than 5–6%. Then you can assume without much error that, well, I can take some value here and say that this is IF. And that, but what about IR? I cannot conclude. Just is a very small value, but how much? It's difficult to say how much. Okay? This is I would say this is a very asymptotic characteristic. The real characteristic of the transistor is not like this, but we can use in some cases this approximation to calculate the value of IF. And we do this. I approximate, I'm assuming that the curve is in saturation. That's it. You do all the time this in bipolar transistor, you have the early effect. I suppose you have heard of it. The early effect, what's the meaning? Oh, the bipolar doesn't have a full saturation, you have something with a slope. But when you bias a given circuit, you assume that the current is the DC current, it's some value here. Maybe 1 microamp or 1 milliamp. But if it moves to 1.05, doesn't matter too much to calculate the small signal parameters such as GM, which is the most important transistor parameter. So why not doing this here as well? Okay. Okay. I have here give you an example, a graphical example of how the specific current of a transistor changes with the gate voltage. Okay, we have made a lot of measurements to characterize this parameter. And you see that, well, if the voltage changes from 0.5 up to almost 5 volts, the specific current doesn't change too much. I would say without much error that it's around 28, 27 nanoamps plus minus 15%. Don't have a large variation here. The whole variation is from 25 to 35. I would say, it's 30 plus minus 5 nanoamps. This is not too much. 5 or 6 is 20% of 30. I would say, it's an average value of 30 plus minus 6%. 20%. You say, this seems to be too much. It depends. Sometimes you operate your device in a very small region of gate values. This is a node technology because it accepts gate voltage of 5 volts. Typical technologies of today accept 1.5 maximum 1.2 volts at the gate. Okay? So the variation of the gate voltage is much smaller than in this case here. So for some technologies, you have approximate values of the specific current or chip specific currents for any MOSFETs and P MOSFETs. You see that there is almost a ratio of 3 from the from the NMOS to the PMOS. Almost 3. This is due to the mobility. You know this from undergrad course, the mobility of electrons is around 2.5 to 3 times higher than the mobility of holes. Okay? This we see here. Look that the Cox is the same for both transistors. Okay? They are processed simultaneously. So the oxide thickness is the same for both. Okay? The end factor, well, it's not much difference. You see that the IS also includes here the end factor. This is simulation, okay? The previous curve is not simulation, it's measured. This is simulation. This is a curve that was obtained in simulating a transistor with a PC model, if I remember. And you show that from minus 150 temperature range, the specific current varies from 4.7 to 6. So the variation is not so large. This is a typical range for design, typical temperature range for design. Another set of curves now. This is what we call the common source characteristic, because the source voltage is constant, and you change the gate voltage here. Look, this is a log scale of currents, because we want to emphasize the exponential characteristic of the transistor. Otherwise, if you put here a linear scale, you just see this. If you put a milliamp scale, or you just see something here if you put a nanoamp scale. So let's use a log scale. You have decades here, 10 to minus 9, minus 8, minus 7, minus 6. So you have decades. This is a log scale, 2 nanoamps, 3, 4, 5, 6, etc. So if the characteristic of the transistor is plotted in a log scale, you have first a linear characteristic because the dependence here is on the exponential. If you logarithmize the exponential, you have a linear scale, right? Log of it, log of e to x is x, right? Doesn't matter if the log is decimal or the period is the same. Natural log or decimal log is, okay? It will be a straight line. When you approach some voltage here, some gate voltage, in this case, when you approach the threshold voltage, the characteristic becomes curved. Seems like, no, it will not saturate, just goes on according to a quadratic law. Okay? This is the characteristic, approximate characteristic of the textbooks of undergrad course. Okay? And now we have the characteristics for all regions. This is what we call an all-region model, because it fits well the exponential region or the quadratic region, or something in the middle, which is the moderating region. Along this, I would say around this knee, there's a kind of knee. So this is the moderate region. So this is very fuzzy. It's not clear. But here you need the two terms of the PCM or the UICM. Okay, this set of characteristics corresponds to this circuit here. Okay? For various values of Vs, the first one, Vs equals 0. So the source is connected to the bulb. Oh. And you have, and under this condition, Vd equals Vg. So you have a short circuit here and a short circuit here. This is what we call the MOSFET configured as a diode. We have a short here, a short here. It becomes a two-terminal device. It's diode. The second one, when you bias the source at 0.5 volts, you see that there is a shift. It's like pulling this curve here, that it will become almost equal to this one. The shape of the curve is much similar. Right? Then 1 volt, 1.5. If you increase the source voltage, you decrease the charge density at the source.
Yes.
Okay, so you decrease the current. Right? Okay, in this condition, when Vd equals Vg, the drain voltage is not important because the transistor is in saturation. I will not explain this right now, but usually under this condition, when the drain is connected to the gate, we have saturation condition. Okay? Okay, let's move to another. This is another set of curves, but in this case, the gate is kept at a constant voltage. Vd equals Vg once again. But now, it changed the source. In the first case, that's Vg equals to 4.8. The first curve corresponds to Vg equal to 4.8 volts. And you see that in this case, when you increase the source voltage, you decrease the exertion charge at the source. Then the current decreases, okay? So if you increase the source voltage, the current decreases. You see, look here, you have a minus sign right here. So if you increase this term, the gate voltage is constant, this one is constant, then this term will decrease, the current will decrease, right? So you have a family of curves for different gate voltage, 4.8, 4.2, etc., etc. This very interesting set of curves is have a set of curves that corresponds to different conditions at the gate. Let me explain what those curves mean. Let's go back to the previous slide. You see here. Now, suppose that I change the gate voltage, okay? Oh, this curve will change. Say that Vg, I increase Vg, then you have something like this. And then if you increase Vg, something like this. Oh, in that set of curves that I'm going to show, I'm going to normalize all the curves to IF. Because I want to put all of them in the same graph. So assume that you have curves such as this one. In that case, Vs will be equal to 0. Okay. And I will show you a set of, I would say, universal curves for the MOSFET. What's the meaning of this set of curves? Well, in this axis, you have VDS or VB, because I will connect the source to the bulb. For each curve, I have a fixed value of VG for each curve. And then I will change the value of VDS, simply VD, because the source. Can you see this? Because the source is connected to the bulb. Then I have a curve, say, for each VG, I have a curve similar to this. If I increase VG, I have a set of curves, ED, ID versus VDS. Now, instead of putting all these set of curves, I have 1,000 curves, say 6 or 7. But these curves will have very different values of currents, say from 1 nanoamp to 1 milliamp. This is a 10 to the 6 difference between one curve and the other. So instead of plotting these curves in a scale in amperes or nanoamps, I simply divide by the current, the drain current by the saturation current. So the maximum of these curves would be 1, the maximum. Of course, each of these curves has a maximum at the IF. So if I divide ID over IF, I will have maximum 1. Maximum value will be 1. Okay? So we plotted some curves for these values of gate voltage, 7, and so on. Okay? Now, for this value of the gate voltage, 700 millivolts, we found a curve like this. Okay? For IF equal to 65, another curve, and so on. And you see that if IF is very low, all the curves are coincident with this one labeled A. Okay? This means that for weak inversion, we have a very small, what we call saturation voltage. The device saturates for very, very low voltage. Because you see that for VDS of the order of 4 phi t, the scale is normalized to phi t, and you have 4 here, 8, 12, 16, 20. For VDS of the order of 4 phi t, the transistor is saturated. This is for a transistor with an IF very low. But this happens also for IF equal to 10 to the minus 1. If IF is less than 1, I would say that all transistors saturate, or all saturation occurs for a voltage of the order of 4 phi t. But now, if the inversion level increases, you have a shift of this, what we call saturation voltage to the right. This is also very important for low voltage designs. Assume that what's phi t? Phi t is 25 millivolts. If you have, for example, VDS over phi t equal to 40, which is this voltage here. You see that this transistor saturates for this one here, saturates for VDS over phi t over 40. This means that VDS approximate 40 times 25 millivolts, which gives you 1 volt. This is 25 millivolts, right? I'm talking about this value of VDS over phi t. So this transistor here, E saturates for 40 phi t. But this one here for around 60 phi t, and the other one for 80, 90 phi t. This means that if you, in most of the cases, you want to operate the transistor in this region, because this behavior in this region is the behavior of a current source. The device operates as a current source. Because in this region, saturation region, the voltage changes, but the current does not change. This is the property of a current source. So in most of the cases, especially in amplifiers, in current mirrors, you operate the transistor, you want to operate the transistor in that region. So if you have a device such as this one, and the power supply is of the order of 1 volt, you cannot put this transistor in saturation because 1 volt corresponds to this point here. And at this point, this transistor operates in this linear region, what we call the triode region or ohmic region. So I will not be able to operate this transistor under this supply voltage as a current source, right? So it's very important to know the details on how the transistor curve changes in terms of VDS. All right? Oh. Okay. I'm going to try to define saturation in more useful terms. How could you define saturation? Okay. So suppose that this is the curve of the transistor, ID versus VD. For a constant VS, for a constant VG. Okay. I'm going to define two slopes, one at the origin. Okay. This is the subject of a future session. And the other one at a generic point, right? Why am I defining this here? I'm including this topic here because there is no real saturation. There is no effective saturation. Then I'm going to define a saturation according to my will, as I want. How could you define, for example? Oh, I'm going to say that saturation occurs when the slope here is 1% of this one. It seems to be reasonable, right? Or 10% if you want, if you wish. It depends on you. And it depends on the application, right? Then I'm going to define two saturations for me. One is for a 1% difference in the slopes, and the other is 10% difference in the slope. This is arbitrary. I don't know if you want to choose another number for this zeta here, it's up to you. Okay, but I'm going to define saturation in this way. Okay, assume that I have defined saturation when the slope of the characteristic is 1% of the slope at the origin. Then I would say that, well, when this occurs, I'm going to define what I call VDS saturation. Then I come here. Oh, this is 1% of this one. I measure this voltage here, and I say that this is VDS saturation. Okay, this is the value of the saturation voltage for the drain to source. Then I come here, and I put this in terms of the inversion level. And I have something like this. In weak inversion, this value is almost constant. Okay? If the inversion level at the source increases, I have something like this. This result here, I don't know if you remember the result of the undergrad courses, VDS set, VDS minus, right? Okay, this is valid for this region here, because a VDS sat proportional to VGS minus VT is approximately equal to VDS sat proportional to the square root of the current. Because the current is VGS minus VT squared, right? This is basic theory of MOSFETs in the strong inversion region. But for weak inversion, look, for weak inversion, the saturation voltage does not depend on the inversion level. If it's 0.001 or 0.01, or up to 1 approximately, the saturation voltages of the MOSFET is around 100 millivolts. Okay? So, designs for low voltage sometimes or most of the time employ transistors in the weak inversion region or subthreshold region. My colleague Carlos Gallo approximated a formula for the calculation of VDS sat. This is, of course, it depends on how you choose saturation, but this is approximate. Let's make a short break. Ei, Mário, já fui melhor tratado, esqueci de brincar. Não, não precisa, eu consigo. 7, 8 minutos, tá bom? Só para descansar um pouco. Eu estou indo muito devagar. Esse passeio para reforçar mas assim vocês dormem muito. Tem que gritar mais, andar mais rápido. Vocês estão mandando algum artigo para o Lascas esse ano?
Sim.
Estão preparando?
Estamos preparando um artigo.
É domingo o deadline, você sabe, né?
Se não consegue, pode ser outro.
Ah, o Ianta. Quando é o Ianta que eu
Acho que o 21 de outubro, ou 25
o
de
deadline, hein?
outubro.
O deadline.
25
E quando vai ser? Em dezembro, o Ianta?
Fevereiro.
Fevereiro. É antes, pouquinho antes do Lascas. O Lascas é final de fevereiro.
Nossa.
Mas o Lascas é mais interessante, né? Tem mais, a comunidade é maior. Tem...
Sim, essa data assim.
A data, o problema. É final de fevereiro, é ruim para você?
Não,
O deadline, não. Sim, a preparação. Porque sempre começamos a preparar em cima da hora. E aí fica para o outro evento.
e agora sim.
Você vai à cantina?
Cantina? A cantina? Sim, em português é muito diferente. Sim, eu me encarrego.
Tá bom. Tá, porque também aí eu teria que levar meu cartão, que eu não tenho, não uso soles.
Sim.
Aqui o pessoal quase não usa mais dinheiro também, né? Só os mais antigos. Seu. Falando nisso.
Olha, não, mas para você usar
Eu vou levar, sim.
este é quase um papel feminino.
Por causa
E a
de...
tua, porque eu tenho lá um pouquinho. Se eu precisar.
Sempre
Mas
tira
assim,
mas em geral o pessoal acho que usa pouco dinheiro atualmente, né?
eu acho é que temos jeitos para pagar como tem uns amigos.
Sim, como agora tem um Pix, tipo Pix, que você faz a transferência no momento. Não é cartão de crédito, é Pix. Não sei como você chama, deve ter outro nome.
Sim, aqui é Plim, já
Plim.
Então, não,
É o
não
equivalente do
precisamos,
Pix.
não precisamos já carregar.
O problema é que você perde o celular. Aí. O celular está descarregado. Então eu teria que andar com o carregador junto.
Tem.
Pois é. Não, por isso que eu sempre gosto de usar dinheiro. No Brasil eu sempre uso. Porque porque eu não gosto de usar o celular. Quando eu vou almoçar onde fomos almoçar, eu sempre pago com dinheiro. Meu filho não. Meu filho paga a minha refeição, aí ele paga com o celular. Aí faz a transferência na hora. Mas eu me sinto inseguro. E eu não gosto, meu celular é muito pesado. Como eu não ando com mochila, como você,
Ou tendo o carro, tipo,
eu não. Então, eu prefiro pagar. Mas realmente a tendência. Por isso, meu filho morou na Suécia há 2 anos, eu acho. Ele nem sabe como eu vivo. Não soube.
sempre eu tomo café da manhã perto, fora dos quarteirões, não? Eu pago, assim, eu pago com Plim.
Quem não se comércio teve que se adaptar naturalmente. Mas é impossível o comércio entender sem
Sim.
o carreta, né? Essa transferência eletrônica instantânea.
E um se acostuma muito, e uma vez com minha esposa, ela tem um filho, o filho dela, íamos ir num zoológico. Mas
O zoológico é do lado da Waka, né? É bonito o zoológico?
Sim, é bom. Esse dia estão muitas pessoas, muitas. Não, é que era o dia da independência do Peru.
Vocês foram num dia muito particular também. Obrigado.
E graças a Deus.
Depois eu pago.
E o detalhe é que muitos falei, não, a gente não vai lá. Vamos a outro zoológico que tem
Sim.
em Guatiba. É mais longe, mas eu pensei, não, vamos. Quando eu cheguei lá, falei, bom, para 2 adultos e um menino. Não, pagamento por cartão, falei, não, já visto.
Não aceita. Só efetivo?
Eu precisava pagar 60 soles. Eu não sei como eu tinha 65. Eu paguei. Então, não tinha grana nem para comer uma garrafa de água.
Era só efetivo?
Eu estava acostumado aqui.
Acho que falta. Então, não, daqui a pouco não tem mais preguiça. Mas
Mas acho que já estamos avisados.
Mas isso foi quando
Há 2 anos. Era uma antiga administração, agora é a mesma administração do zoológico daqui, por lá, eu, tomara, já sei que o pagamento pelo pagamos, eu me senti infeliz, porque eu nem conseguia cuidar que eu não sei.
e qual é a distância de Lima?
E que esse fica,
Ao norte? Sim.
não, ao leste.
Leste.
É, mais ou menos. Se é uma distância
Mas
que será uma hora.
é outra província, né?
Não, ainda é Lima, mas é que eu tentei procurar outra opção, porque eu vi que estava muito cheio. Eu, como já o rapaz, a gente prometeu levar ao cinema.
Que idade tem?
Na época ele tinha, não,
Nossa.
não, você sabe, sou
Passaram cedo.
E depois, quando a gente foi embora daquele zoológico, no primeiro posto de combustível, eu vi, tem uma delícia, vamos a comer aqui, tomar água. O almoço esteve muito bom o almoço.
Viram tanto? O que você comeu?
Era uma carne, eles chamam carne mechada.
É bovina. Bovina.
É que não sabia o que vocês pediam, eu queria ter o mesmo que vocês.
Não, estava muito bom. Também era massa, pasta com frango.
Com frango.
Tinha um pouco de tomate, cebola. Bom, o frango muito bem saboroso.
Aqui tem muita comida de frango, muita peixe. Carne bovina não.
É muito mais caro a carne bovina.
Porque não são como o Uruguai, como o Rio Grande do Sul, que tem muito gado. Lá no Brasil, onde fica o rei do gado. Só um pouco, mas na novela, meu Deus, quando eu assisti essa novela, navegando, eu ficava maravilhado com a quantidade de
Eu tenho muita terra propícia para. Infelizmente, tem muito gado de história. Mas que uma vaca requer mais ou menos 1 hectare. Ali não. Imagina. Você tem 100 vacas, deu 1 quilômetro quadrado. Né? Eu sempre procurando evitar a carne dele, apesar de eu apreciar muito. Porque a filha dele é vegana. Não, ela também tem muito respeito pelos animais. Acho que é mais.
também do jeito como mato,
É muito.
nas cordilhas e todo.
Os povos.
Vem aqui pelas nossas atividades.
Tem douradas?
E macabres mesmo.
No Brasil, não sei por um negócio chamado farra do boi. Eles soltam o boi e vão brigando com o boi, e o boi fica louco. A gente tem boi que às vezes se atira num penhasco dentro do mar, assim, tão apavorado de tudo que é expressão. E na época de Páscoa, isso. Tem alguma data, não sei se é. Não sei se é. Isso da Ilha da Mangueira, não sei, é ali no litoral de Santa Catarina. Mas cada vez eu acho que está diminuindo, porque o pessoal está tem proibições, às vezes a polícia também vai e pega.
Por exemplo, aqui as corridas dos bois diminuíram muito.
A cor do boi?
Os cafeinadores, acá presente, isso.
Ah, não, isso
Vai
foi,
facilitar.
isso já foi, já está quase morrendo.
Mas foi banido oficialmente?
Não, esse aí nunca foi sabido, assim, não pela maioria da população.
Não,
Sim.
já não.
Você faz um espetáculo X, e ninguém vai.
É bom.
Esse
Com consciência, então, da população.
podemos fazer.
Sim,
Isso não dá. Então,
Isso.
não dá aquele.
Nossa, isso aqui, vocês, embora estão fazendo agora correr do bois, mas não querem, não matam não, um bichinho.
Mas era como aquela de pamplona que solta o animal? Não, você fala de tourada. Tourada, né? Com pano vermelho, com as leis, tourada.
Porque se for o negócio com a pamplona,
Mas
o
também-
risco é do homem.
O homem mas o animal
Foi
fica
bater dentro do cara.
o animal fica muito estressado. Não é tão fala assim, vai ficar o animal de uma forma muito bruta.
Eu acho que ele mexe com
Aquele, quase, ele não sabe, não sei, 2 milhares. Não.
Bora, então. Adelante.
Sim, sim.
Ok. Ah, now, I have 2 or 3 slides to explain the regions, 2 regions, say the weak inversion and strong inversion region. 2, I would say, asymptotic regions. In one of them, the weak inversion region, the important term is the log term. Okay? Just to recall that in weak inversion, this inversion level is much less than 1. Okay, if this IF is much less than 1, this term here becomes equal to approximately -1. Okay, and the natural log term can be also simplified because if you recall this square root of 1 plus x when x is much less than 1 is 1 plus x over 2. The approximation of square root of 1 plus x. X for x much less. 1 plus x over 2. Okay? So in this case, this term becomes approximately equal to I over 2, right? Then I can move this -1 here, and I have an expression which is this one. So ID is an exponential function of Vg over n phi t, and an exponential function of minus Vs over phi t. Once again, you should note that the dependence of Vg is less than the dependence on Vs. Okay? And this expression can be written such as in this way here. Right? Just algebra, but of course, if VDS equals 0, the voltage difference between source and drain zero, the current is zero, right? Okay. Now, using this expression, we can build these three curves. The first one is ID over IF, okay? IF is this term here, versus VDS, VD minus VS, okay? So you have something which has an exponential dependence on VDS. If VDS increases, this term decreases. And if VDS tends towards a large number, the argument of this function becomes very negative, and the exponential becomes much less than 1. So you can remove it and say that, well, for high VDS, the current tends to saturate. Okay? There is a note here, if VDS over phi t equals 3, okay, the current is 5% of the saturation curve, at 5% of the saturation curve. Okay. Okay, the second curve, the first one is for VG and VS equal to constants. Some constant, doesn't matter. The second curve, you have the dependence of ID in terms of VG. Note that the dependence of ID in terms of VG is an exponential function. So the author define the y-axis in terms of log ID over I0. So you have a straight line in which the slope is 1 over n. Okay? And finally, dependence of the current in terms of Vs. Put the negative sign here because, well, the dependence is on minus Vs over phi t. So we inverted here the Vs in order to have a positive slope. Just this. Okay. So you have first the current in terms of Vd at Vg and Vs equal to constant terms. The second one, log of ID over I0 versus Vg. The exponential dependence must, but with a slope equal to 1 over n. And finally, the dependence of ID over I0 in terms of Vs. This is a very famous professor, Professor Eric Zitos from Switzerland. He's a very well-known guy. He worked for the watch industry and also at the EPFL. He has a lot of courses on the transistor model. He's one of the co-authors of the famous model of the MOS transistor, which is called EKV. EKV are the initials of the authors, are the familiar, in fact, are the familiar names of the authors. Hence, V, K is for Krummenacher, and V is for Vitos. This is a model very similar to ours, very similar to the ACM, EKV model. It has written, published a lot of papers about, especially about low power design, low voltage design. Well, what about the strong inversion model? In the strong inversion model, you neglect the natural log term. You have this term here. And in fact, the model that I'm going to show is similar to the model of the textbooks, where the textbook don't take into account this term -2 and 1, because the square root of IF is much higher than 1 for strong inversion. Okay, so here we have the combination of the two currents forward, which depends on the conditions at the source. The conditions at the source depend on the gate and then the source voltage. And the conditions of charge of the drain depend on the gate voltage and also on the drain voltage. And you note here the symmetry once again. If you exchange source and drain, you have the same result with a different sign. You just change the sign of the equation. Okay. So the shape of the curves is such as this one. In this case, the saturation voltage is approximately equal to VT or VP, which is VG minus VT over N. This is a difference. There's a difference between this model here and the model that is used in the textbook and does not appear in textbooks on the grad courses, right? You can also plot the square root of ID in terms of VG. The textbooks say that ID is a function of VG minus VT squared, right? So if this parabolic function were true, you would have a linear graph of square root of ID versus VG, right? And the intersection of this line with the G-axis would be VT 0. Okay, but in practice, this is not true because you have something like this. The current doesn't go to 0 if VG equals VT 0. No, this is not true. And you also have some distortion of this straight line for high voltage because the mobility is a function of the gate voltage. And mobility decreases with the gate voltage. So the factor N is also a function of VG. So you have a distortion here. I'm explaining this here because in the past, the community used to determine the VT0, extrapolating this curve of the transistor. But this is not simple because you can extrapolate this region here. Oh, this is complicated because you have some distortion. Or you could extrapolate the curve for higher gate voltage. Oh, but this would give a different VT0. So this is not correct for the extraction of the threshold voltage. We need some other methods that give us a better result for the threshold voltage. So in the past, they used, say, the strong inversion model to determine the threshold voltage. But the strong inversion model doesn't fit all the operating regions. It's just a small region. And what should be the interpolated straight line here or here or here? You have difference. How do you choose the point where to extrapolate the curve down to the threshold voltage? So this should be avoided, right? There are several methods to determine the threshold voltage. They give some difference, but they give the approximate value of the threshold voltage. Okay? The same happens when you plot square root of ID versus DS. It's also a square dependence law. And here is of course, the ID right here increases with increase of DS. Okay? Okay, let me explain now the determination of the pinch-off voltage. Okay, this is the circuit to determine the pinch-off voltage. What's the problem here? Oh, you should know the IS of the transistor, but you can estimate the value of IS from the technology. Let me show you again the expression of the specific current of the transistor. IS mu, say it's an NMOS transistor, so it's mu N. Let's assume that I have a square transistor in which W equals L. So W over L equals 1. And this is also assumed to be a very, very large transistor, a very, very wide transistor. Okay, let's assume that, say, for example, 10 microliters and 10 microliters. Oh. Assume that you also know the technology parameters. Okay. Say you have what we call the PDK of the technology. The PDK gives you information about the technology. So what's the mobility? The mobility is, say, 400 square centimeters per volt second. Say. Let's assume this. This is given, yes. Let's say that this is 2 femtofarads per square micrometer. Let's assume that this is true. What's N? N I don't know. I can estimate 1.2, for example. Okay, but I can also make some simulation, but the simulation is here, or the measurement is here. Well, what's phi t? Phi t is K T over Q. This is the universal constant, Boltzmann's constant. Q is the electronic charge, the elemental charge. 1.6 10 to the minus 19 coulombs. The constant. And this is the absolute temperature. What's this? Measure the room temperature and add it to, say, what's the temperature right now? Maybe 17 degrees centigrade. So this will be around 300 Kelvin. 209, 300 Kelvin. It doesn't matter too much. The difference is only 3% from one to the other. So it's not too much. So let's assume that we know this. Okay, I would say 100 nanoamps. It's around this. It's not much difference from 100 nanoamps. Then I need an equipment right now, a current source. Okay, but usually a laboratory like mine or maybe like yours has several current sources. So you can calibrate this current source. You can use 300 nanoamp current source. And then you connect your transistor with connect the drain to the gate. And then you connect the source to a DC voltage source. And now you change the voltage source, the source voltage. Okay? So then you change the source voltage, and you measure the gate voltage. So this axis is the gate voltage. And this axis is the source voltage. And in this case, the source voltage equals the gate voltage. Let me explain this using our model. Okay, first explanation. In this configuration, the transistor operates in the saturation region. So ID is equal to IF. Okay, ID equals IF minus IR. This term is much less than IF. IF. And this is IS times IF. Okay. Now I'm going to use the UICM. Let me show you the equation of this UICM. Vp minus Ps over phi t equals square root of 1 plus IF minus 2 plus square root of natural log of square root of IF minus 1. Okay, look, in this case, ID equals IF equal to VIS, right? Okay, then we can say that IF is 3. Okay, now if you substitute this IF with 3, we conclude that have 4 here minus 2, okay. 2 minus 1, the natural log of 1 is 0. 0 plus 0, okay. So using this circuit, you find that Vs equals Vp. Oh, this is the way we use to determine the pinch-off voltage, which is equal to. So then, for each Vg that you measure here, you have a correspondent Vs. Okay? The inversion level of the transistor is always equal to 3. This is not very accurate because you can say that, oh, but the IS of the transistor, this is nominal from the technology. You don't know if the device that you build is exactly as would be predicted by the technology. You have some fluctuations. Secondly, this value depends on Vg. So you would need to calibrate the IS for each Vg. Of course, the difference in the IS when Vg varies is not very large. Okay, as I showed you, plus minus 20%. So this is a quite acceptable way to determine the pinch-off voltage in terms of the gate voltage. What happens when Vp equals 0? When Vp equals 0, when Vs equals 0, we have Vp equal to 0 as well. Right? Vp equals to 0 means Vg equals Vg minus Vt zeros over n equal to 0. This is a way to measure Vp. threshold voltage. So when VP equals to 0, VG equals to VT, it is 0. Okay? This is not the method that we currently use to measure the threshold voltage or the pinch off voltage. Now, if you take the derivative of VP versus VGB, this is of range. Okay, so you have this curve here. Now take the derivative of this curve in terms of VG. You have the inverse of n. So the slope is smaller here, you have a higher n. N is right here. When the slope increases, the value of n decreases. Okay? This is the way that we measure n. Let's say the first method to measure the value of the slope factor. And you measure the slope factor in terms of the gate voltage. In fact, this value is a function of VG only. And we have determined the n dependent on the gate voltage using this method, this simple circuit. Okay, this is a summary of our equations that I'm going to use some circuits that we have designed, right? The first one is this circuit here. This is a kind of a MOSFET divider, voltage divider. Okay. Okay. This is a series association of two transistors. This association is biased through this current source. Okay. The current source injects a current equal to I into this series association of transistors. Okay. Of course, these two transistors are transistors of the same technology. Okay. Are two transistors with the same VTs, but with different geometries or different aspect ratios. Right? Explain this now because it's really important. We have designed a lot of circuits using this configuration, which is really, really very useful. So we have a bias current. Bias current is I. Two transistors. Look here, the gate to drain connection of one of the transistors. This one is what we call M2, M1. I'm going to represent the substrates just to emphasize that both substrates are connected to the ground. Okay. Okay. These two transistors are different with respect to the aspect ratio. Okay. Now that the aspect ratio of a transistor is W over L. Okay? But in this case, that let's assume that S1 and S2 can be different. Maybe they are equal, but they can be any value in principle. Okay? So S1 equals W over L of transistor 1. S2 is W over L. 2. Okay, now I'm going to write the transistor for both M2 and M1. So ID2 equals IS2 IS2 minus IR2. Okay? I would write the same equations for transistor 1. Of course, I have differences in the specific elements, and maybe in IF1. ID2 equals, of course, there is no gate current. So this current is the same as ID2, which is also the same as ID1. Okay, so the current is the same for the two transistors. So this equals I. But the first transistor has the gate connected to the drain. So I could say that IR2 is much less than IF2. If this is the diode connection, once again, this is true for transistor M2. But for transistor M1, I cannot say that this IR2 or IR1 will be different from be much less than IF1. In fact, I'm going to show you something right now. Oh, you see that the current is the same in both transistors, through both transistors. Now, what's this IF2? IF2 are associated with the source of transistor 2, right? And IR1 is associated with the drain of transistor 1. Okay? But note here that the equations for IF2 or IR1 are the same. Let's put it here. Because this node is the source for this transistor. But the node is the same as the drain of the second transistor. So what this means that this term is the same for the source of transistor 2 or drain of transistor 1. Then I can conclude that IF2 equals IR1. Okay, because see, this node sees the same set of voltages. So the normalized forward and reverse current story, this is the most difficult concept to understand when I talk with my students. And I ask this concept in the exam. They always make mistakes about it. In general, they assume that, oh, IR1 is much less than IF1. No, this is not true. This is like, I would say, a long transistor in which you are watching this node here in the middle of the channel. Okay, it's almost like assume that these two transistors are equal, two equal transistors, the same width, the same length. So this is like a long channel transistor in which you have access to the midpoint, the mid node. Okay, so but if you substitute in the equations, the difference here is that this is the source of the transistor and the drain of this. But this voltage here is shared by both equations of the CCM. And look, the gate voltage is the same as well. Therefore, I would say that the inversion charge density at this node is the same for both of these. Okay? Then you can say that, well, IF1 or IR1 equals IF. So let's rewrite this expression like this. This is ISH times S2 times IF2. And the second expression, I can rewrite it as ISH times S1 times IF1 minus IF2. Now, using these two equations, I can find the relationship between IF1 and IF2. Let's divide these two equations. So S2 IF2 equals S1 IF2 equals 1 plus IF2 equals fine. From this equation, you see that the inversion level IF2 of this transistor 2 is lower than the inversion level of this transistor 1. If you understand this, the remaining calculations are a consequence of this here. Okay? But you can say that IF2 is a fraction of IF1. But this node here it's going to be labeled as Vx. Okay, Vx. What's Vx? It's a kind of a voltage division between this node and this node. I would say you could imagine that this is a series of resistors. This is not true because these are quite nonlinear devices. These are not resistors. Okay. Now I can use algebra and calculate this voltage in terms of IS2. Okay, and recall that. Now I can recall that. What's IS2? Well, I can use this equation here and say that IF2 is A over IS2. And I know this IS2 because it's a technology and geometry. Okay, this is the bias current. I is the bias current. It's a current source that I have in the laboratory, for example. IS2 is a parameter which depends on the technology and on the transistor. IS2 equals IS A times W over L of transistor. This is what I call S2. Then I have an equation to find the value of Px. Okay, this equation here is simply a derivation of the UICN. I use the equations for the two transistors, I subtract them, and I get this result. Just 2 minutes. Let me explain how I obtain this result here. I have the equation for transistor M2, this one, Vp minus, at this node, the voltage is Vx. This is the source node of this transistor, right? Vp minus Vx over phi t equals to, well, square root 1 plus natural log 1 plus f2 minus 1. Now, the equation for the forward current of this transistor is Vp minus 0. The source is at 0. Square root of 1 plus f1 minus 2 plus natural log square root of 1 plus f1 minus 1. Okay, now I subtract equation 1, this one, from equation 2. Vp's are eliminated and remains Vx over phi t. Is this term minus this one? Okay. What happens here? This IF1 is 1 plus this term here, I called alpha. This term here, IF1. Okay, this is what I call alpha. 1 plus alpha. This is alpha. IF1 equals alpha IF2. Then I have here 1 plus IF2 minus this term here, plus natural log of this term, minus, I can put it right here. It's a difference of natural logs. I can put as a quotient of That's it. Well, this is our relationship. Okay. And I'm going to use this relationship to show you something very interesting. Okay. And look here, this IF2 is simply I divided by IS2. Well, I know I is the current that is injected into the series association of transistors, and IS2 is a technology and device dependent parameter. Okay, I know both, so I know the value of IS2. So I know everything here, and therefore I know how Vx relates to phi t. Okay? And I'm going to show you a very simple example. Assume that this term is much less than 1. Then this cancels out with this one, almost cancels out. And this one remains here. But now alpha IS2 is much less than 1. I can once again approximate the square root of 1 plus x, which is 1 plus half of x. And you find out that this is the result if the inversion level is very low. This means that for very weak inversion here, you have an X voltage, the intermediate node voltage is proportional to the temperature. The temperature phi t is proportional to the absolute temperature. This would be useful as a temperature sensor because you have here the information of temperature, the absolute temperature. Okay. Okay, let's stop here because some students did have classes, I suppose. Okay, thank you. See you tomorrow. Same time, same place. Ah, no, pela Lubanda.